Welcome everyone to your last introductory biostatistics lecture. It's a bittersweet day, I'm sure, for all of you, and me as well. We're going to have a regular length lecture today, and then afterwards going to see the first handful of poster presentations for the brave few people who've signed up to do their presentations early. So it'll be a fun day. And in lecture, we're going to cover finally two continuous variables. So my apologies to any of you who chose to do some other data set for your project that involved analysis of two continuous variables that you were just finally getting into it today. But I guess for those of you who did, you'll have a head start on lecture today. So we've covered a few different cases this semester. We covered the case of two categorical variables. And we're thinking generally about our variables either as response or predictor variables. So response variable being something like an outcome, the result that we're interested in, and a predictor, which is something that we might think is causing a change in that response or outcome variable. And even though with the methods that we're using this semester, we don't know about causality, we're showing correlation unless it is an experimental study, of course. For observational studies, we're not showing causation, but we still think about it in terms of the response and the predictor. This affects how we plot it if there are continuous variables. So when we had two categorical variables, this was the day that Professor Wyka came in, and I believe she talked about the race and the death penalty example. This was the topic for odds ratio, chi-squared test, and a lot of you for your projects. And then right before that, where we had the situation of a categorical predictor and a continuous response, or sorry, right after that, this was just last class, was when we covered analysis of variance. And what we're covering today is the case where both the predictor and the response are continuous. So instead of, we used frequency tables to summarize as descriptive statistics for two categorical variables. We used box plots, bar plots for the case with one continuous outcome and categorical predictor. The kind of bread and butter plot now is the scatter plot. Start with some examples. I went to PubMed and looked up correlated. I looked up Pearson correlation and just saw what came up in PubMed. Here's one example of, I don't know, some big words. I don't know exactly what they mean, but they're talking about some chemical used to disinfect drinking water and it's the effect of its byproducts on T24 cells. So the results here are talking about cellular GSH level. I don't know exactly what that is, but it's something that's measured an activity in the cell on a continuous variable, and the ROS production and cellular GHT activity. Point is that these are continuous variables. They're things that are being measured both with the drinking water disinfection and the result on cellular activity. See, here's another one, validation of the quality of life in life-threatening illness, family care version, in German-speaking carers of advanced cancer patients. Boy, so point here is that it's got a wide variety of applications, but let's see, what's the result here? Pearson correlation between test and retest lay at 0.92. So they're giving a test twice and seeing how correlated the results between just replicates of this quality of life test are. And let's see, as expected, a significant positive correlation was found with hope and significant negative correlations with traumatic stress, depression, anxiety, and overall subjective burden. So in this case, we have, these are all, I don't know, what do you think? Are these hope, traumatic stress, depression? Those are either response or predictor. And the other thing is, let's see, this quality of life, this quality of life measure. So which one's the response? What's the predictor here? I'm going to guess that the quality of life measure, the subjective quality of life measure, is the response variable, and these other things like hope, traumatic stress, depression are the predictor variables. So so you'll notice that there are some that have a positive correlation. So hope positively correlates with subjective quality of life, and traumatic stress and depression negatively correlate with quality of life. So this is the point of the Pearson correlation measure that we're going to do today to quantify this relationship between two continuous variables and say whether they are positively correlated with each other or negatively correlated or uncorrelated. One more example, we've got folic acid supplementation. Effect of folic acid supplementation on homocysteine levels in children taking anti-epileptic drugs. And this one is a randomized controlled trial. So let's see, correlation correlation was tested by Pearson correlation, but what was the response and predictor? We've got folic acid tablets and THCY levels. So we have on the one hand the amount of folic acid supplementation, and on the other hand these THCY levels, this homocysteine levels. So the p-value was less than 0.005 was the cutoff for statistical significance, and the result here is no increase. So it's another example here. We have these homocysteine levels, something quantitatively measured. It's in something like milligrams per ml of blood, and amount of folic acid supplementation as the predictor. So the applications make sense. The point is that they're two continuous variables, and we want to know if there's a relationship between them. We want both a subjective description of how strong any association is, and we want a statistical significance test to tell us whether that's more than you would get between two unrelated variables. So again, the scatter plot is what we're going to use for visualization, and this Pearson's correlation is the numeric measure that we're going to use to summarize the relationship between these variables. It only summarizes the linear component of this relationship. I'll show you some examples of what that means, and it does not have to do with causality. It just has to do with association between the variables. If you switch your response and your predictor variable, it will not change your calculated correlation. So here's an example, a few examples of linear relationships. This is a positive correlation. This is a negative correlation. This one is a somewhat stronger correlation because more of the variation in one of the variables is explained by variation in the other. And then here's a couple examples of nonlinear relationships as viewed on a scatter plot. So when when you can draw a straight line and all of the points are contained fairly closely to that line, that's what we would call a very strong relationship between those two variables, in that they move very closely together. When the lines that you would have to draw to capture all of the points are further apart, like on the right here, that's a weaker relationship. Any questions so far? This all seem pretty thumbs up? Here's a couple examples of no relationship at all. So by no relationship, it means that knowing about the value of x doesn't tell you anything about the value of y. It also means that if you were to draw a line that minimizes the distances to all the points, it would be more or less a horizontal line. Not exactly, because there's noise in the data, but close. Yes?
Is it possible by vision to say that maybe that the reason there's no relationship because there's no dependency from y and x, because where does that mean?
Yeah, there's no obvious dependency between y and x here. So knowing something about x doesn't tell you anything about y. Whereas going back here, if you know x is small, you know y is smaller too. If you know x is large, you know y is probably large as well. So, you know, you can actually do really well just visually with scatter plots. There are some cases where the scatter plot can throw off your intuition, but you should be able to look at a scatter plot and have an idea of whether there is an association between the variables. And it's important to do. You'll also be able to do a linear regression in SPSS or Excel and get your correlation coefficient and your p-value, and that'll tell you something, but it won't tell you as much as looking at the scatter plot. Here's a real example of a regression: diphtheria, polio, and tetanus immunizations in a number of different countries plotted against under 5 mortality of children under 5 years old. So we've got countries: Bolivia, Brazil, Cambodia, Canada. So we've got some poorer countries, some wealthier countries. We look at a wealthier country like Canada, you've got 85% immunized, China 94% immunized. And then you've got the under 5 mortality rate in Canada, only 8%, or sorry, 8 per 100,000, I assume that is. And in China, 43 per 100,000. So looking at the scatter plot, you can see that clearly there is some relationship here, but it doesn't explain everything. And especially as you get into the countries with high percent immunized, there's a lot of variation in that under 5 mortality. And that's because there are other causes of, there are other causes of under 5 mortality than diphtheria, polio, and tetanus, even though that's probably a measure of the robustness of the public health system in that country to some extent, but it doesn't go all the way. So this correlation coefficient that I've been talking about so far, what is it? Well, it measures the strength of a linear relationship between 2 continuous variables. We use rho, as usual, the Greek letter, to describe the value for the population, and r for the sample. So if you estimate it from just a sample, you're going to use r. And this is sometimes just called the correlation coefficient. More precisely, it's Pearson's correlation coefficient. There are a few different correlation coefficients that can be used. The one we're talking about today is Pearson's correlation. What is it? Let's take a look at this for a moment. this is how you would calculate the correlation. Take a look at this for a minute and imagine that instead of X and Y, these are both X. So X is exactly Y. It's just the same variable. So then what is this? This would be X minus the average of X, and then it would be that squared. So it would be the sum of all of your data points minus the mean squared, the sum of squares, right? Do you remember when we used that before? For standard deviation? Yep. Yeah, when we divided that by n minus 1, that was the variance. Now take a look here. We're dividing by the standard deviation squared. So, so if this were just one variable, it would be standard deviation over standard deviation. You'd get a value of 1. And that is, in fact, if you calculate the correlation coefficient of any continuous variable with itself, the answer you will get is 1. That's a perfect correlation or a perfect association between those two variables because they're the same variable. So knowing the value of one variable tells you exactly the value of the other variable. And they don't actually have to be exactly the same. All they have to be is a constant multiple of each other. So the correlation, if we took everyone in this classroom's weight in pounds and then took everyone's weight in kilograms and calculated the correlation between those two measures, it would be 1, because it's the same thing just on different units. And to calculate it from a sample, it's almost the same thing, except for this factor of n minus 1, which was like when we were calculating the standard deviations. That's the degrees of freedom rather than just the sample size. So that's how you calculate it. You're not going to probably, maybe you'll calculate it by hand in the lab. It's not difficult to do, but you can, even if you're usually doing it with SPSS. But the useful thing I think here is just being able to kind of look at this and see how it's almost an equivalent of calculating the variance, but it's between two different variables instead of just the variance of a single variable. So just to help give you a bit of intuition about what Pearson correlation coefficients look like, you should probably be able to take a look at a scatter plot and kind of estimate in your head approximately what the Pearson correlation is. If it looks like this, that's -1. So they're perfectly described by the linear relationship, but as one goes up, the other goes down. That's a Pearson correlation of -1. On the other hand, if there's some scatter around that line, then it's no longer a correlation of 1. This case, a correlation of -0.6. In this case, where the best fit line is approximately horizontal, there's a correlation coefficient of 0. And then on the other hand, if your best fit line has a positive slope, that's a positive correlation coefficient. And if there's no noise at all around that line, that's a correlation coefficient of 1. Here's a quick intuition question for you. A correlation coefficient of 0.3, do you think that's going to be statistically significant? And what do you think it'll depend on if you're going to answer that question? Yeah, it'll depend on your alpha, but so let's say we fix alpha. Let's fix alpha at 0.05. Is a correlation coefficient of 0.3 going to give you a p-value less than 0.05? That's a good answer. I saw your facial expression is kind of like, apologies to the online people if you couldn't see my facial expression. But what do you think? Does that seem statistically significant or not? No?
I don't know. Isn't there a table?
Yeah, there is a table. We'll learn to use the table later, but what do you think that it's going to depend on when you use that table? Ah, very good. The size of the sample. So yeah, you know, the exact same correlation of 0.3, if you only have maybe 4 data points, that's probably not going to be significant. But if you have 1,000 data points, that's going to be highly significant, that same Pearson correlation. So there are 2 things that are going to affect your p-value for the linear association between 2 variables. One is the strength of the association. So, you know, if your R is closer to 0, then it's harder to detect that association compared to when the true association, like that row, the population value, if that's close to 1, it's easier to see the association, but it depends on your sample size. So you could have a correlation of R equals 0.02, you know, almost no correlation at all. But if you have 1 million data points, that could still be highly significant. It's like everything else we've done in class, and that a smaller association can be significant if you have a large sample size. And I kind of brought that up as discussion because I saw this interesting teaching statistics paper recently and something I should probably incorporate eventually, but it asked students and faculty to estimate the p-value from scatter plots, and showed that most beginner students could not estimate the p-value from scatter plots, but that people with more data analysis experience got better at estimating the p-value by taking into account both the strength of the association and the sample size. Yes. Right, so what's the tipping point of statistical significance? I mean, if you're close to the tipping point, then you're not going to be able to tell by eye. You know, if it's a p-value of 0.04, it's going to be pretty hard to say by eye. But in cases where it's extremely significant, you'll be able to tell by eye. So if you see, like, when I look at this, I can tell that pretty obviously looks statistically significant. I think this looks pretty clearly statistically significant as well, in that, you know, it doesn't look like this association occurred randomly to me. I don't know, do you disagree? Maybe it's a little bit fuzzy in this case, but so yeah, you know, there's not exactly a tipping point, but the point is that with some experience of looking at plots and doing the analysis, you start getting a feel for what looks like an association, and that's useful because then when you start seeing things like nonlinear associations, or something where there is an association but it's being lost because of an outlier in your data, you can still look at your data and have some intuition about what's going on. because the statistical tests that we're giving you, they have no intuition whatsoever. Only you have that. So the Pearson correlation coefficient, the population one rho and the sample one r, they're unit free. So regardless of whether your variables are in kilograms or grams, or one is kilograms and the other one is centimeters, Pearson's correlation is unit free. It's between -1 and 1 inclusive, with negative values being a stronger negative association, so an inverse relationship, and positive values being a positive association. So it's a nice intuitive kind of metric in that no matter what your variables are, the interpretation of Pearson's correlation is the same. Contrast that to, we haven't gotten to it yet, but if you've had any experience with a linear regression and you have a slope, you remember, right? There's, when you draw a best fit line, it has a slope. That slope has units. By way of example, if you did you know, the association between people's height and weight, there would be a positive association, and you could write that down as something like, for every inch taller someone is, they on average weigh another 10 pounds or something like that. So those are units. That's like 10 pounds per inch. But if you turn that into a correlation, then the units are gone. And we saw that, remember, in the formula. It's because you're dividing by the standard deviation, which has the same units as the variable itself. So that's what gets rid of the units. And a correlation coefficient close to 0 means that there isn't much of a linear relationship. Here are a few cautionary notes. Unless your correlation is exactly 1 or -1, then a high correlation does not necessarily mean you have a linear relationship. You'll need to look at the scatter plot to see that. But if you can have a curve, a linear relationship, so something where there's definitely a curve in the relationship of the data, and still have a Pearson correlation of like 0.8 or 0.9. So it doesn't mean, it means that there is a linear component, but it doesn't mean that that entirely describes your data. A high correlation does not imply a causal relationship unless that's the case because you did an experimental study and you're actually controlling one of the variables. And just with the means and the standard deviations, it can be sensitive to outliers. And there are examples where you could have 50 data points with a correlation of 0, and then one super outlier point that could bring your correlation up to 0.8. That can happen. So all of these, you know, the linear relationship and outliers are things that are best assessed by looking at your scatter plot. So we can do a hypothesis test, just like you're getting good and comfortable with on the Pearson's correlation. So we'll set it up like other tests, with a null hypothesis of no correlation in the population and an alternative hypothesis that there is a correlation. And then this is kind of neat. You calculate this thing. So it's just sample size n-2 over 1 minus Pearson correlation squared. Take the square root of that and multiply that by the Pearson correlation coefficient again. And this is kind of weird, but it just turns out that under the null hypothesis of no association between the variables, it's t-distributed with n-2 degrees of freedom. So how about that? If you are given, even if you don't have the data, you're given the Pearson correlation coefficient and the sample size, you can do your hypothesis test. You can go ahead and calculate, you could use this to calculate a p-value, or the way we've done it, you could compare it to the critical value from the t-table and say whether or not this is a statistically significant test. And like we expected, as n gets larger, t grows. It gets larger, it's more likely to exceed your critical value. You're more likely to reject the null hypothesis for the same value of r. Yes?
To go back to your cautionary notes slide,
Mm-hmm.
is that like the same thing as correlation and not causation?
Yes,
Oh, okay.
it's exactly that. Correlation does not prove causation.
Sorry, I once saw some statisticians did all these crazy graphs of like number of cows in Sweden versus like infant mortality rate, like just stuff that had like really good correlation,
Right.
but clearly were unrelated.
Yeah, I think I saw that too.
Yeah.
Like, yeah, number of cows in Sweden against infant mortality in Zimbabwe or something like
Right.
that this statistician had just gotten by data mining of like a whole bunch of stuff and looking for spurious correlations. Yeah, no, that's exactly what this is. Correlation doesn't imply causation. And when people say that correlation does not imply causation, they are usually not referring only to Pearson correlation, but any of these measures of association that we've used. So like the t-test, the z-test, the chi-squared test, all of those, the association does not imply causation, unless it's an experiment where we know that if there's an association, it must be causal. Good example. Okay, so that's correlation. Correlation, you will notice from that formula that I gave you and just from the discussion that it does not matter which is your dependent and which is your independent variable. All it is a measure of association between the two, and if you switch the two, you get exactly the same value of r. Now, regression analysis is related to correlation, but it's a little bit different in that it does matter which one is your dependent and which one is your independent variable. And it's going to allow us not only to say something about the strength of association between these two variables, but also to make predictions about the value of your dependent variable for any given value of the independent variable. So you're gonna create a regression model for predicting your dependent variable or your response or outcome variable. So simple linear regression, so-called, it just means that we have two variables, just one dependent and one independent variable. And that's in contrast with multiple linear regression, which we don't get to. That's if you're in epi-bios, you get to that in your next course after this, where you have more than one independent variable. So we only have two variables, and that relationship between them is going to be described by the slope, which has to do with the association, the intercept, which is kind of the starting point of the dependent variable, and then there's random error, which we also call residuals. So you've got your predictable part of the relationship and the unpredictable part. we're going to use uppercase letters like X and Y for the random variables. So we're talking about like height and weight in the population, and lowercase with subscripts for each of the individual observations. Here is a population regression model. So the dependent variable y is equal to the intercept plus the slope times the independent variable plus this error term. So this is how we represent the relationship between the independent and the dependent variable in a simple linear regression. This last thing is just an alternative representation that's saying that this is just another way of thinking about it. The average or expected value of y conditional on or given a certain value of x is, well, using this up here, it would be beta 0 plus beta 1 x. So that's saying that you have a certain expected value, and it's assumed that there's a random error term then around that. Any questions? All right, so that was for the population. So even in the population, there's the random error term, the component that of the amount or the component of y that is not explained in the linear relationship with x. Now, for the sample, we're going to estimate a regression model that will look like this. So we will have coefficients b0 and b1, the intercept and the slope. And when we plug a value of x, our independent variable in, it'll give us a predicted value for y that we put a hat on to say that it's estimated or predicted. And the differences between this y hat and the actual observed values of y are going to be our errors or the residuals. And here's what I mean by that. So here is a set of XY data points with a best fit linear regression. And what is plotted on here, these lines, are those individual errors or the residuals. So you'll notice that they're vertical, right? I mean, you could potentially draw a shorter line going straight to the line, but the residuals are the amount by which y is off, so they have to be vertical. Yes?
We're basically just calculating the curve.
Yeah. Yeah, you're going to estimate the straight line from your sample. You're going to draw it, and then you're going to then the next step that you would do would be to look at your residuals, and I'll talk about what the assumptions are of a linear regression, but you would check to see that the assumptions of your model hold by looking at the residuals. The important thing to remember about residuals is that they're these vertical lines. They're differences between your actual and your predicted value of y for each of your actual xy pairs. This line, the way we'll normally draw it, is found by your software by minimizing least squares. So you sum the squares of each of these errors and find the line that minimizes that sum of squares. That's called least squares. Very, very common method for all sorts of regression, not just simple linear regression. So B0, the slope, that is the expected value of y when x is 0. So it doesn't always make a whole lot of sense if it was like the relationship between height and weight for individuals, then it would be the expected height of someone with 0 weight. So it doesn't always directly make sense, but that's how you would interpret the intercept. And B1, the slope, is the amount in which y changes for a change of 1 unit in x. So it depends on the units of both y and x. If it's the relationship between height and weight, it depends on whether height is in inches or feet or centimeters, and it depends on whether weight is in pounds or grams or kilograms or whatever. All right, it's not like correlation in that sense, in that it does have units, and if you change your units, then the value of it changes. So it's not quite, it's not interpreted just as a measure of the association, it's a measure of how much y changes for a change of 1 unit in x. So you remember the class last time on analysis of variance? Well, we kind of do that with simple linear regression as well, in that we've got a few sums of squares that we add up. We've got a total sum of squares, which is just, if you were to take, this would be like your horizontal regression line, meaning your line it's just horizontal, it's put at the average value of y. So this would be your residuals in that case, just each value of y minus the mean, and you sum them. So that would be the sum of squares of residuals in a null model with no slope. And that is equal to the sum of these two parts. One is the sum of squares of your errors. So these are the residual terms, the ones that I plotted on the last one. And then the other part is the part that is explained by your model. So this is what's not explained, this is what is explained. And the is explained part is the predicted values minus the overall mean. So let's take a look on this plot again. These are the errors. Let's say the mean is right about here. Now for this point, what is the component of that sum of squares of the regression? So this is the error term, and this is the amount that's explained by the regression from here to here. Right? So we're saying that this is the total amount from which data point 6 differs from the overall mean. There's the component that is explained by the regression, and then the component that is not explained by the regression. And this is saying that when you square those and add them up, you have this relationship. And this is important because it's related to the correlation coefficient and to this thing that we call the coefficient of determination, or R squared. So the sum of squares of the regression divided by the sum of squares total is this R squared value. And this is a very common measure of association used in regressions. Unlike R, it's never negative. It's only between 0 and 1. But it has this nice interpretation. So looking at this, does someone want to phrase for me what that that interpretation is. So the sum of squares of the regression divided by the sum of squares total. If you were to think of this as if you were to think of this as a variance, how would you put this into words? Yep.
Well, if they're looking at, would it be telling us how much variation is not due to the relationship? Or
Almost. This sum of squares of the regression is the amount of variability that is due to the relationship between the variables. So it's the fraction of your total variability that is explained by the regression. So it's kind of a nice intuitive explanation. If your regression line accounts for 100% of the variability, then this is 1. If your sum of squares of those regression differences are only half of the total variability, then you would say 50% of the total variability is explained by your regression. Still just talking about linear relationship here. Yes?
Does that just mean that it's telling you how accurate your line of regression is?
Yeah, it is a measure of how accurate your line of regression is. Because if you have all of these data points nice and close to the line, then your sum of squares of the errors is going to be small, and your sum of squares of the regression will be very close to your total sum of squares. So a value close to 1 means you have a very accurate regression. It explains almost all, means that your regression model explains almost all of the variability in Y. It might bear mentioning that in cases where you have once you get into multiple regression, when you have a lot of variables, it's possible to get an R squared close to 1 due to overfitting. You're just overinterpreting the data. But in a simple linear regression, that's not really an issue unless you have only 3 data points. And a value close to 1 really does mean that your variability in X explains variability in Y. So unless you have a bunch of values above the mean and a bunch below, so
meaning that they, I guess they even out in terms of how far away they are from the regression line.
So an R squared close to 1, an R squared close to 1 means that your points can't be very far from this line. And it means that that these differences of the line from the overall mean, so like this, this. So I'm drawing here these are the Y hat minus Y bar that I'm drawing. And those have to account for almost all of the variability if R squared is close to 1. So you can do that both by having a larger slope so that these values are larger, and you can do it by having the data points be closer to the line. Both of those will increase your R squared. So it's the sum of squares that are explained by your regression divided by your total sum of squares. And it has this nice relationship to the Pearson correlation in that the Pearson correlation, as you calculated before, if you square it, it's the same, you get the same thing as your coefficient of determination. So I've shown you two totally different ways that will both give you the same r squared. I don't quite know how that works. I'm sure if you took that formula that I gave you for r and worked it out, you would find eventually that it's the same as this formula. Kind of neat. It's not totally obvious to me that it should be that way, but it's nice that it does turn out that way. So you might wonder, why do we have a coefficient of determination then? Because it has less information than r, right? Because r could be positive or negative, but r squared, you've lost that sign. So why have r squared? One reason to have r squared is that you can apply it to multiple regression. So if you have several predictor variables, you can still calculate an r squared even though you can't get an r. And another is this interpretation that r squared is the percentage or the proportion of total variance that is explained by your regression model. That's another reason. But r squared does not tell you anything about whether you have a positive or a negative relationship. Oops. So there's a couple r squareds. One, not surprising, right? It's no longer +1 and -1. Now it's just 1 for both of those. Here's a couple somewhere in between. I don't know, maybe 0.25 or something like that. And an r squared of 0. So remembering back, you can tell that r squared is 0 here, right? Because it's just horizontal. So unless it were somehow placed somewhere other than at the mean, which it isn't going to be, then all of those differences in the regression prediction from the overall mean are going to be 0. So your sum of squares of the regression is 0. There's no relationship, or no linear relationship at least. There are some assumptions involved in doing a linear regression. The first one being linearity, in that the model that we are using is only modeling a linear relationship between x and y. Once you get into multiple regression, it is possible to still use a multiple linear regression for nonlinear relationships. And you do it by adding terms for things like x squared, x cubed, so that the coefficients are still linear coefficients, but it's like you're creating a new variable that captures some nonlinearity in the relationship. This funny word, homoscedasticity, which we've assumed before, that the variability of the errors doesn't depend on where along your plot are. So it means that your residuals on the left-hand side of the plot are about the same size as the residuals on the right-hand side of your plot. And that's something that's best assessed by looking at, there are these things called diagnostic plots, which you can get from SPSS or any software. By the way, the diagnostic plot, what it often looks like is just actually plotting your residuals against x. So instead of, so on here, you can actually see what it would look like. You know, here are your residuals. And you can kind of see by looking at this that the residuals are about the same on the left as they are on the right. So that is a good homoscedastic relationship. It's a little bit harder to tell when you have a line. So the way it's usually plotted when you're doing the test, one of the ways is just by plotting the residuals as a function of x. So you're subtracting the amount of subtracting the regression predictions so that you get a bunch of horizontal residuals. Approximate normality, so that is to say that your residuals are normally distributed. And that's something that is easy to assess. Once you have the residuals, you can make a histogram, just look at them, see if they look normally distributed. There are special plots for doing that as well that you will see in your regression output. And independence, which we always assume that each of the observations that we have are independent. This is just a compact expression that actually contains all of these assumptions. That is to say that the errors being normally distributed, that's saying that the errors for any value of x are the same, right? It's if homoscedasticity were violated, then the errors would have to be different for different values of x. So don't worry about the equation too much, but this is what your linear regression equation, the results of your linear regression, this is what it's estimating. This intercept, this slope, and then also your residuals as a byproduct. So this is kind of neat. As long as those assumptions are met, then your slope and your correlation coefficient are related to each other, and they're equal just with a difference of this factor of the standard deviations of y and x. So if you were to take your correlation coefficient, which is between -1 and 1, multiply by the standard deviation of y, divide by the standard deviation of x, that gives you your slope. How about that, right? All these different things, and they're all almost the same thing, even though we came at them from different angles. Same thing for the sample. It's just the only difference between the slope and the Pearson correlation coefficient is the ratio of the standard deviations of the two variables. So if both of your variables have the same standard deviation, then your slope and your Pearson correlation are the same thing. How about that, right? So if you're talking about, I don't know, heights of I don't know, correlation between heights of identical twins, most likely heights of twin A and twin B, in each of these, there's no reason they should have different standard deviations. In that case, your slope and your Pearson correlation are going to be the same thing because they have the same standard deviations. Things you can impress your friends with your statistics knowledge at a party. And in addition to that relationship between the Pearson correlation and the slope, you can do inference tests on both. I showed you how to do the hypothesis test for the Pearson correlation. When you do a linear regression in SPSS, it's going to do a hypothesis test on your slope. And it turns out that the results of those two tests are identical. They're the same thing also. Doesn't matter which you do. Also pretty weird. I don't really understand why that is, I'll be honest. I just think it's neat. And this is conversion to z-score. That's just one way of making sure that they both have the same slope. So if they both have the same standard deviation of 1, then your slope and your Pearson correlation are identical. Here's just a little cheat sheet for you to help out when you have, when you're doing a bivariate analysis. You want to look up, you know, the type of data, continuous, rank, or categorical, and you have any of these goals that we've done just to help you look up a method to use. And I've added to this some equivalents. So, you know, we've learned paired t-tests, ANOVA, Pearson correlation, all these things. There are what we call non-parametric alternatives to these, which we didn't have time to get to in this class. But when your assumptions about the distribution, like your assumptions of normality, are violated, you can often go over to this non-parametric alternative, and that will be an option in SPSS. It doesn't help you get around your assumption of independence. You still have to make, you still need independent observations. But if your assumptions of normality are extremely violated, or homoscedasticity, you can go over to the non-parametric alternatives. So congratulations, that's all the statistics that I'm going to force you to learn. I hope it's been fun, and I hope that seeing everybody's projects is going to be fun, and that you might learn a little bit more statistics through all of that. And I would like to thank all of you who've been dedicated at coming either in person or online, and to remind you to please fill out these teaching evaluations. I don't want to have a situation where there are only like 6 people who filled out the evaluation. That looks really bad for me. Hunter College teaching evaluations are important, so those are taken very seriously when I eventually go up for tenure and promotion. So you know, that's the main thing I ask of you after all of the classes and everything here, is just go ahead and fill out the teaching evaluation, and I will read every one of them, and I take them seriously for future semesters. And if you have negative things to say, I will account for that in future semesters. If you have good things to say, then it makes me feel good about myself, and I appreciate that too. So thank you. Let's take a couple minutes and start getting set up, the few of you who are presenting your posters today, and then we'll do the posters, and after that head downstairs to the lab. And I'll see if I can find Tony. I'm hoping he's going to come up here and look at them as well.